Welcome to Calculus 1, Chapter 3, Section 6. Chapter 3 is about differentiation rules, and in Section 6 we're going to talk about derivatives of logarithmic functions. And there are a couple of aspects to this conversation. The first one is going to involve just some basic rules, the patterns of taking the derivative of a log and a natural log, and then we're going to look at equations that are a little bit more complicated where we could use rules like the product rule, quotient rule, chain rule in order to take the derivative of an equation that says y equals, but I think we're going to find it considerably easier if we take the natural log of both sides of the equation, use some of our properties of logarithms in order to expand the complicated side of the equation, and then we'll apply our logarithmic differential rules. Oh, let's just go have a look at it. So to start things off, let's start simple. I will just kind of cruise through a couple of these slides, so if you would like to look at these, you're welcome to. A reminder about the graph of the logarithm function, y equals log base b of x. And then here we're seeing a couple of our initial rules or properties. The first one says that if we're taking the derivative of the natural or the log base b of x, that the derivative is equal to 1 over x times the natural log of b. I could prove that to you. I could use the change of base property and write this as natural log of x over the natural log of b, and then we could use the chain rule, and I promise you it's going to turn out to equal this. And more specifically, remember that natural log is the same thing as a log with base e. And Sophie is in the house. For those of you who have not met Sophie, say hello, Sophie. So natural log is the same thing as a log with base of e, which is why the right-hand side of equation number 2 does not have a natural log in the denominator. Because if it did, it would say natural log of e. Of course, the natural log of e is equal to 1, so really there's an invisible times 1 in the denominator of the right-hand side of equation 2. And then we move into equation 3, or bullet number 3. And what that says is it sort of incorporates the chain rule by using a couple of different notations. We can either use U notation, the letter U, or we can use, she has no regard for personal space. We can use U to represent the inner function, or we can use G of x to represent the inner function. And we could take this property that we're seeing in number 3 and apply it back to number 1, but really what number 3 is an application of taking the natural log of a function. So it's a more detailed version of equation number 2. And what we see is that if you're taking the derivative, of the natural log of a function, then the result is 1 divided by your inner function times the derivative of that inner function. So I've circled the heck out of that, and Sophie is pushing buttons on the iPad. Don't do that. So I've circled the heck out of stuff in the left-hand side, but the right-hand equation says the same thing. Instead of a u, you're seeing g of x. So you've got 1 over your inner function times, it's 1 over your inner function, if my pen will work. Come on now. Sophie, did you break it? I'm switching pen colors. I'm getting no love. There it is. All right, Sophie's now eating the power cord. Gotta kick the cat out. Come here, babe. Come here. Come here. Go find your sister. Play with her. Go on. Sorry. All right. In this equation, if we take the derivative of the natural log of g, the result should be 1 over g of x times the derivative of the inner function, g of x. What we're seeing here is they've simply multiplied this into this numerator, so you're seeing g prime of x over g of x. You may use whichever notation works best for you. So let's take a look at an example. This example wants us to find the derivative of the natural log of x. So sine of x is our u value or our g of x function. And when we take the derivative of this, I'm seeing after my equal sign, I see 1 over my inner function times the derivative of my inner function. The derivative of sine is equal to cosine, so we're seeing 1 over that original inner function, 1 over sine x, times now cosine of x. And if we take this cosine and we multiply it into the numerator times the 1, we end up with cosine over sine, which is equal to cotan. So it's been simplified down to cotan. So that's the easy part. The next part is still easy, so to speak. I guess everything's relative, but this logarithmic differentiation method is most helpful when you're working with equations that are more complicated. So the right-hand side of this equation has a fraction in it, so we could be using the quotient rule. The denominator has a function to a power, so we would need to use the power rule and the chain rule when the time comes to take the derivative of the denominator. In the numerator, we would have to use the product rule because there's multiplication happening between x to the 3/4 and the square root of x squared plus 1. And we would use the power rule here, and we would have to convert this square root into a power of 1/2, use the power rule, and apply the chain rule here, all as part of taking the derivative of the numerator. That sounds like a real mess. If you would like to try that process of using all of the other differentiation tools that we've talked about previously, specifically product rule, quotient rule, chain rule, power rule, to try to take the derivative of the right-hand side of this thing, you can do it. I say try it. Then you can compare your answer to what we get after this process. What's happened here is we've taken the natural log of both sides of this equation, and when you take the natural log of the right-hand side, what happens is the power rule for logarithms the product rule for logarithms says that I can turn this multiplication into addition. And let's get it all on the screen there. And that would be this addition symbol right here. So let me number those. There's number 1 and number 1, if that's helpful to you. Now, this x to the 3/4, that power of 3/4 is appearing in front of the natural log of x. These are all the idea of what's happening here, these sort of properties of logarithms, or specifically the natural log that we're using right here, is covered in college algebra, and it's the process of expanding a natural log by using properties of logarithms. Product rule, quotient rule, power rule for logarithms. If you need to be refamiliarized with those, please look up the power rule, product rule, and quotient rule for logarithms. It goes back into an algebra class. You should be able to find videos and examples of that kind of stuff. I'm sure that on my channel somewhere, I have examples of that also. I've just created over 100 videos recently, so I just can't keep them straight anymore. Okay, so what else is happening? Right, on the right-hand side, this first factor up here, since it's in the numerator, it ends up being positive. The second factor in the numerator also ends up being positive because it's attached by multiplication. This factor that's in the denominator, since it's attached to the numerator by division, it gets a negative as its coefficient. The square root symbol that's up here turns into a power of 1/2, which gets brought in front of the natural log like a coefficient. That is this 1/2 that you're seeing here. And finally, this power of 5 that's related to the denominator, that power, as part of the power rule of logarithms, is also coming in front of the natural log as a coefficient. So if you need to relearn some of that stuff or get refreshed on it, please do so, because that's going to show up in the homework assignments and on your exam for this chapter. Once we've totally decomposed the natural log of the right-hand side of that equation, we start taking the derivative. The derivative of the left-hand side of this equation requires us to be mindful of implicit differentiation, which we've talked about in this chapter. So the natural log of y is the inner function. So what we see down here is 1 over the inner function times the derivative of the inner function. Now I don't know what the function y is, so it's almost like we're just putting a little note there, dy over dx, that says we're taking the derivative of y with respect to x. We don't know what y is, but we're taking the derivative of it, or we will eventually. In fact, that's what we're going to end up solving for. So we're going to see that dy over dx stay right there. On the right-hand side of the equation, our coefficient of 3/4 comes down. The natural log of 1 over x, as we saw in a previous slide, is equal to 1 over x. Here's the plus sign coming down. Here's the coefficient of 1/2. And then we've got the natural log of x squared plus 1. The derivative of that equals 1 over the inner function. So here's the 1 over x squared plus 1. And we have to multiply by the derivative of the inner function. The derivative of x squared plus 1 is 2x. So we multiply that into the numerator. There it is. The minus sign comes down. The 5 as a coefficient comes down. And then we take the derivative of the natural log of 3x plus 2, which equals 1 over the inner function times the derivative of the inner function. The derivative of 3x plus 2 is just 3. So we see that all combined there. I keep repeating myself using the same phrase in the hope that it will become almost like muscle memory. And if you need to say it out loud, I don't know if you should say it out loud while there are people around. You're going to look like a crazy person talking to yourself. People think you're crazy for taking Calc 1 already, though, so run with it. The derivative of the natural log of a function is 1 over the inner function times the derivative of the inner function. Or if you want it to say the natural log of u equals 1 over u times u prime. Or you can say the derivative of the natural log of g of x equals g prime of x over g of x. Whatever it is, put it on a flashcard, say it a bunch of times, get it stuck in your mind, because you're going to be using it a bunch, especially in this section. Now, the goal of this problem is to solve for dy over dx. So on the right-hand side of the equation, inside these parentheses here, we see that things have been cleaned up a little bit. The multiplication of numerators and denominators has been completed already. We're not finding a common denominator, so you're still seeing 3 separate terms. However, there's no longer a 1 over y on the left-hand side. We've multiplied both sides of the equation by the reciprocal, y over 1, or just y, which is the reason that you're seeing this y right here, and you don't see the 1 over y here anymore. Now our answer is supposed to be in terms of x. We're not supposed to have any y variables on the right-hand side of this equation. Otherwise, we're done. We've solved for dy over dx. But what's up with the y value? Do we know what y equals? We sure do. This is our y value. So we're going to substitute the right-hand side of that equation in place of this y value right here. And we're just going to take that big glob of a right-hand side of the equation, and we're just going to put it in there, wrapped in parentheses. Oh, they didn't even, this author hasn't even put it in parentheses. Could, if we wanted to, not necessary, but just realize that that is your y value. This is not a lesson on distributing or combining like terms or anything, so we're not going to multiply this thing out. If you needed to find dy over dx for a specific x value, you would just plug the x value in. And that is the process of logarithmic differentiation. I'll just put the first part of that next slide on there. Those are some steps. Very generally speaking, all of that algebraic manipulation that we just went through really adds up to these 3 steps. You take the natural log of both sides of your equation and use the laws of logarithms. It says to simplify, but what you're really doing is stretching all of that stuff out. You're tearing apart the right-hand side of that equation using the properties of logarithms, or the laws of logarithms, as it says here. And then we use the rule that we learned at the beginning of this lesson about how to take the derivative of the natural log of either x or a function. Derivative of a natural log of a function equals 1 over the function times the derivative of the function. And then we had to multiply both sides of this equation by y in order to solve the equation for y prime, or in our case, we were using the notation dy over dx. So that's it. That's the lesson. Let's go and look at just a couple of other examples where we will work them out from top to bottom as part of a homework assignment that I'm going to be so generously giving to my students. And let's just try a couple of these. Let's see, I took some notes on which ones I want to work out here. Let's do number 1 and number 8. So number 1, differentiate the function. In other words, take the derivative. Well, the first thing I'm seeing is that I've got a product here. I've got a coefficient. So I have to use the product rule to take the derivative of my first term. And then the derivative of this thing is going to be easy. So let's get to it. F prime of x is equal to, now I'm going to factor the 6 out, and then I'm going to take the derivative with respect to x of the rest of that. That's x times the natural log of 2x. The 6 only got factored out of there. Well, we could take it out of the last term. I'm not going to. I'm just going to take the derivative of 6x, and I'm going to write it as 6. And then I'm going to turn off the ringer on my phone. Silence. Okay, now let's take the derivative of this product. So this is equal to 6 times, I'm going to keep my first factor, the x, and then I'll multiply by 1 over the inner function, which is 2x, times the derivative of the inner function, which is 2. Product rule then says plus. We'll take the derivative of the first factor, which is a 1, times, keep the second factor the same, that's the natural log of 2x. Close that up, keep the minus 6. And then we'll do some simplifying. Oh, that's interesting. Look at this. This 2 cancels with this 2, and this x cancels with this x, which means this entire term turns into a 1. Don't just cross out the whole term and think that it turns into a 0. Really what that term says is 2x over 2x, and anything divided by itself is equal to 1. You don't just cross it out and make it totally disappear. And then I'll multiply the 6 in times that 1, which gives us a 6, plus, then this 6 also has to multiply all the way over to here to this 1 times the natural log of 2x. So that's now going to be 6 natural logs of 2x. And then on the outside of our square brackets, we had a minus 6. Now, as we transition to the next line, which is going to end up being our solution, this positive 6 and this minus 6 are going to actually cancel each other out. Now, those turn into 0. Anything minus itself equals 0. And our final answer is 6 times the natural log of 2x. And that's a pretty straightforward problem. We're using a couple of the previous tools that we've seen, or maybe even only one. Well, the idea of taking this 6 right here and factoring it out of that first part of the expression, that was one of the things that we learned very early in this chapter. And then the product rule, of course. Otherwise, the chain rule is kind of built into the process of taking the derivative of the natural log of 2x. When we multiply, the derivative of the natural log of 2x was equal to 1 over 2x. That's normal. But then when you multiply by the derivative of 2x, that's really you implementing the chain rule. So we had to multiply by 2. Number 2, if you just want to, if you're one of my students and you want to jot down a couple of notes about how to solve these problems, I'll just give you a little bit of a head start on some of these. Number 2 is a chain rule problem. You've got the sine of a function. So you'll have to take the derivative of the outer function, so the derivative of sine equals cosine of 3 natural log x, and then you'll have to follow it up. Chain rule says multiply by the derivative of 3 natural log x. Problem number 3 is you could go ahead and do this as a quotient rule problem. It should be pretty easy. It's just the natural log of x. Your other option is to rewrite this as 5 times the natural log of x to the negative first power. So you could use the power rule and the chain rule. You could try doing it both ways and see if you get the same answer both ways. It should work. Just remember that when you use the power rule here, the negative 1 is going to multiply out front. You'll decrease this power by 1, and then you'll still have to multiply by the derivative of the inner function, which is the natural log of x. Problem number 4 is a product rule question. And then when you have to take the derivative of the natural log of 7x, there's a little bit of a chain rule built in there. You will have to multiply by the derivative of 7x as part of taking the derivative of the natural log. Problem number 5 is more complicated. So you will have 1 over your inner function. And then you'll have to multiply by the derivative of that inner function. In order to do that, you're going to have to use the product rule, because this says x times, and then it's being multiplied by a square root. I would rewrite that as x squared minus, in my case, x squared minus 12. I'd put that in parentheses, raise it to the 1/2 power. When you take the derivative of x squared minus 12 to the 1/2 power, the 1/2 multiplies out front. You've got to keep the x squared minus 12. You have to decrease the exponent by 1, which makes it a negative 1/2. And then you have to multiply by the derivative of the inside of that function. So you're still going to have to multiply by another 2x. So these problems get more complicated by nesting the rules that we have to use. So you end up with rules upon rules. Such is life. Once you're done with all of that, because you started out taking the natural log, or taking the derivative of the natural log, which means that the inner function, we said, ends up in the denominator, you may be able to reduce or simplify that to some extent. So be aware that if you just try to type in a raw answer, it might be wrong because you haven't simplified it at all. I mean, just over here, I'm seeing that this 2 that's in the denominator here would cancel out with this 2 that's ends up in the numerator. Things like that you will want to tidy up. This negative exponent, make it positive and shove that thing into the denominator. Do you have to rewrite it as a square root in the denominator? Not necessarily. You could probably leave it to the power of positive 1/2. Just make sure it goes into the denominator. For that matter, when that ends up in the denominator, it's going to interact with this square root of x squared minus 12, which is to the 1/2 power. So you'll have x squared minus 12 to the 1/2 power over here and over here. You'll want to add their exponents together, but you're supposed to know how to do that, so you use those algebra skills. Product rule, chain rule, power rule, that gets you the first derivative, and then you're going to have to take the derivative of that derivative in order to get your second derivative. Product rule means you're going to end up with some addition that's happening in that problem when you get to the first derivative, and then the second derivative. You're looking at the quotient rule. Well, the x squared over the 8x is going to simplify. So make sure you simplify your first derivative as much as possible, and that should make taking the second derivative that much easier. Number 7 just takes, normally we make problems more difficult by adding stuff, adding processes to the beginning of the process. In number 7, we tack on a little something to the end of the process. We want to write the equation of the tangent line to the curve at this point. The steps involved in solving this one require you to take the first derivative, so find y prime. And remember that y prime is equal to m, the slope of the tangent line, the rate of change, rise over run, dy over dx. So find y prime of x, and then evaluate y prime of 4. So plug a 4 in there, and that's going to give you the slope of your line. Now you'll have a slope and you'll have a point, which allows you to use point-slope form. I'm not going to tell you what point-slope form is. It's not y equals mx plus b, I'll tell you that much. If you don't know what it is by name, you need to know what it is by name, so go look that up. Plug in your x1, y1 values and your m, and you'll have the equation for your tangent line in point-slope form. Then you're going to have to distribute and move a little something around in order to make that equation into slope-intercept form, y equals mx plus b form. That's the form of the equation that they're looking for an answer to this problem. So make sure you answer in the correct form. And then number 8, which is the other one I want to do with you and write it all the way out, is best accomplished by using logarithmic differentiation. So I'm going to start out by taking the natural log of both sides of my equation. Gives me the natural log of y equals the natural log of x to the 4x. Left-hand side stays the natural log of y equals. On the right-hand side, I'm going to use the power rule for logarithms. And if you want to write a little note right here that says power rule for logarithms or just power rule, you may. And I'm going to write that as 4x times the natural log of x. It's almost like that 4x came out front like a coefficient in front of the natural log. You don't have to write that multiplication dot there if you don't want to. It's just kind of a habit for me, I guess. I like that it kind of separates the 4x from the natural log also. Now I'm going to take the derivative. So put a little note over here that you're taking the derivative of both sides, d over dx, the derivative with respect to x. On the left-hand side is where we're using implicit differentiation because we don't know what y is. So I'm going to write that as 1 over y times the derivative of y with respect to x. So that's 1 over y, the inner function, times the derivative of the inner function. We just can't take the derivative of the inner function because we don't know what that inner function is yet. We don't know what y is. On the right-hand side, I'm going to keep my factor of 4 out front, and then I'm going to apply the product rule just to the x times natural log of x. I'm going to keep my first term, or my first factor. I'll multiply by the derivative of the natural log of x, which is 1 over x. Product rule says plus. That is a plus. It's the derivative of my first factor now, which is a 1. The derivative of x is equal to 1 times the natural log of x. So I'm keeping my second factor. Let's simplify the right-hand side and distribute multiplication by 4. And I'm going to write the left-hand side of my equation now as 1 over y times y prime, just switching up my notation, equals 4 times 1 equals 4. 4 times natural log of x makes positive 4 natural log of x. And finally, I'm going to multiply both sides of the equation by y. In order to get rid of that 1 over y on the left-hand side, it will then appear on the right-hand side, and y prime will equal y times 4 plus 4 natural log of x. This is your final, oh, it's not your final answer yet. We still need to plug in our y value. And the original problem tells us that y is equal to x to the 4x. So y prime is equal to x to the 4x times 4 plus 4 natural log of x. This is your final answer. And that's a 4. It's not too bad. Once you get refreshed on the properties of expanding using your logarithm rules or laws, power rule, product rule, quotient rule, you spread out that logarithm on the right-hand side, and then just don't forget to multiply both sides of your equation by y, and then plug it in. You should be all set. All right, that is Chapter 3, Section 6. Problem number 9 is similar to what we just did. You'll use the logarithmic differentiation again. Just take it slowly and remember, refresh your memory on those properties of power rule, product rule, and quotient rule for natural logs. All right, that's it for this section. I will see you in section 7. Thanks.